Welcome to an in-depth exploration of fluid behavior at the microscale, where intuition from everyday life completely breaks down. In channels just 50 micrometers wide, fluids behave in ways that seem almost magical compared to what we experience in everyday life. To understand microscale flow, we must start with the most important dimensionless number in fluid mechanics, the Reynolds number. The Reynolds number is defined as density times velocity times characteristic length, divided by dynamic viscosity. This number represents the ratio of inertial forces, which want to keep fluid moving, to viscous forces, which resist motion. At high Reynolds numbers, we get chaotic turbulent flow with swirls and eddies. At low Reynolds numbers, flow becomes smooth and laminar, with fluid moving in parallel layers. For flow in pipes, the critical transition from laminar to turbulent typically occurs around a Reynolds number of 2,300. Now let's perform a scaling analysis to understand why microchannels fundamentally change fluid behavior. The Reynolds number is directly proportional to the characteristic length L. This is the key insight. When the characteristic length shrinks from millimeters to micrometers, the Reynolds number drops by a factor of 1,000. This graph shows how Reynolds number decreases linearly as we reduce the characteristic length scale from millimeters down to tens of micrometers. Let's calculate actual numbers for water flowing through a 50 micrometer channel. First, we need the properties of water at room temperature. Water density is 1,000 kilograms per cubic meter. Dynamic viscosity is 0.001 pascal seconds. A typical velocity in microfluidic devices is 1 millimeter per second. Our characteristic length is 50 micrometers, or 50 times 10 to the minus 6 meters. Substituting into the Reynolds number formula, we get 1,000 times 0.001 times 50 times 10 to the minus 6 divided by 0.001. This gives us a Reynolds number of just 0.05. This is extremely low. A Reynolds number of 0.05 is thousands of times below the turbulent transition, meaning viscous forces completely dominate. What does it physically mean when viscosity dominates over inertia? Think of it like ants walking in perfectly organized lanes, rather than a chaotic crowd pushing and shoving. In laminar flow at the microscale, fluid particles move in perfectly organized parallel lanes, never crossing between layers. At this scale, any momentum that might create instabilities diffuses away through viscosity faster than it can accumulate and grow. The flow becomes completely deterministic and even reversible. If you reverse the flow direction, particles trace back their exact paths. For laminar flow in circular pipes, we can derive an exact relationship between pressure drop and flow rate. The Hagen-Poiseuille law states that pressure drop equals 8 times viscosity times length times flow rate, divided by pi times radius to the 4th power. Notice the incredibly strong r to the 4th power dependence. Having the radius increases pressure drop by a factor of 16. Let's calculate pressure drop for a 50 micrometer diameter channel, 1 meter long. The radius is 25 micrometers. Flow rate equals velocity times cross-sectional area, which is 0.001 times pi times 25 micrometers squared. This gives approximately 2 nanoliters per second. Substituting into Hagen-Poiseuille, we get this expression for pressure drop. This gives approximately 12,800 pascals, or about 1/8 of an atmosphere per meter of channel. Even though the Reynolds number is tiny, microchannels actually require significant pressure to drive flow due to viscous resistance. Here's a critical question. Why can't we just stir fluids at the microscale to mix them? Stirring in everyday life works because it creates turbulent eddies that rapidly transport fluid parcels across the container. But at low Reynolds number, turbulence simply cannot develop no matter how fast you try to move a stirrer. If you inject a blob of dye and let it stretch along the channel during forward flow, then reverse the flow direction, and the dye blob retraces its path and reconcentrates back to its original position. This remarkable behavior would never happen in turbulent flow, where mixing is irreversible. Let's do a rigorous scaling argument to quantify when viscosity beats inertia. The inertial force per unit volume scales as follows. Inertial force scales as density times velocity squared divided by length. The viscous force per unit volume scales differently. Viscous force scales as viscosity times velocity divided by length squared. Now let's take the ratio of these two forces. The ratio of inertial to viscous force is exactly the Reynolds number. This confirms Re is a correct dimensionless parameter. The key insight is that when L shrinks, viscous forces grow as 1 over L squared, while inertial forces only grow as 1 over L. One of the most striking demonstrations of microscale behavior is the Y-shaped mixer. When two fluids meet in a Y-shaped microchannel, they flow side by side without mixing. The interface remains sharp for centimeters. The two streams flow side by side, maintaining a sharp interface between them. There is absolutely no turbulent mixing across the interface because turbulence cannot exist at such low Reynolds numbers. At the microscale, molecular diffusion becomes the only mechanism for mixing. The diffusion coefficient for small molecules in water is about 10 to the minus 9 square meters per second. The time for diffusion to mix fluids across a distance scales with the square of that distance. Diffusion time equals length squared divided by diffusion coefficient. For our 50 micrometer channel width, let's calculate the diffusion time. We get about 2.5 seconds for molecules to diffuse across the channel width. Compare this to the convection time through a 1 centimeter long channel. At 1 millimeter per second velocity, this takes 10 seconds. At the microscale, diffusion and convection times become comparable, which never happens in everyday life. The ratio of convective to diffusive transport is captured by another dimensionless number, the Pecklet number. The Pecklet number equals velocity times length, divided by diffusion coefficient. For our 50 micrometer channel example, the Pecklet number is 50, meaning convection is 50 times faster than diffusion. When Pecklet is much greater than 1, convection dominates transport along the channel. But since P is only 50, not thousands, diffusion remains significant for mixing perpendicular to the flow direction. One of the most bizarre consequences of low Reynolds number flow is time reversibility. When Reynolds number is much less than 1, the Navier-Stokes equations become time reversible. If you inject a blob of dye and let it stretch along the channel during forward flow, then reverse the flow direction, and the dye blob retraces its path and reconcentrates back to its original position. This remarkable behavior would never happen in turbulent flow, where mixing is irreversible. These principles have major practical consequences for designing microfluidic devices. Engineers cannot rely on turbulent mixing and must instead design devices that maximize diffusion. Common strategies include increasing interfacial surface area, using serpentine channels or split and recombine geometries. Serpentine channels increase residence time, allowing more time for diffusion to complete the mixing process. The velocity profile in microchannels takes on a characteristic parabolic shape. For circular channels, velocity as a function of radius equals maximum velocity times 1 minus r squared over r squared. The velocity is maximum at the center and goes to 0 at the walls, creating this smooth parabolic profile. This happens because of the no-slip boundary condition. Fluid velocity must match the wall velocity, which is 0. For this parabolic profile, the average velocity across the channel is exactly half the maximum velocity. When fluid enters a microchannel, it takes some distance to develop the full parabolic profile. The entry length is defined as the distance required to reach fully developed laminar flow. Entry length is approximately 0.05 times Reynolds number times diameter. For our example with Reynolds number 0.05 and diameter 50 micrometers, entry length is just 125 nanometers, essentially instantaneous on the scale of the channel. At such low Reynolds numbers, entry effects are completely negligible and flow becomes fully developed almost immediately. There are two main ways to drive flow in microchannels: pressure and electric fields. Pressure-driven flow, which we've discussed, produces a parabolic velocity profile. Electroosmotic flow, driven by electric fields, produces a nearly flat, plug-like profile. Pressure-driven flow on the left shows parabolic profile, while electroosmotic flow on the right shows flat plug flow. The flat profile of electroosmotic flow is advantageous for reducing dispersion and keeping sample bands sharp. Let's summarize the key scaling laws that govern microscale fluid behavior. Reynolds number scales linearly with length. Pressure drop scales as 1 over radius to the 4th power. Diffusion time scales as length squared. Peclet number quantifies the competition between convection and diffusion. These fundamental scaling laws explain why the microscale is qualitatively different from our everyday experience. The microscale represents a genuinely different regime of fluid mechanics. Viscosity completely dominates while inertia becomes negligible. Turbulence becomes impossible, and flow becomes deterministic and reversible. Mixing can only occur through molecular diffusion. You cannot rely on mechanical stirring. This requires engineers to completely rethink their strategies for manipulating and mixing fluids. The world of microfluidics, where Reynolds number is much less than 1, operates by completely different rules than our everyday fluid experience.